Well, thank you, Ricardo, and thanks to the people who organized this presentation and the workshop. I'm really sorry I can't be there physically, but it's great that people have taken the trouble to set up this remote presentation. So, as Ricardo says, I'm going to be speaking this morning about the surface brightness of galaxies and the evidence against the concordance model. I'm going to start out by talking about the work that Ricardo, I, and Renato Falamo have done about the Tolman Test for surface brightness. Now, this is a very simple test that was developed 85 years ago, or proposed 85 years ago. In a non-expanding universe, or any non-expanding space, surface brightness, which is the ratio of the apparent brightness to the apparent surface area, is a constant. If a source moves twice as far away, it's 4 times as small and 4 times as dim. So the ratio is a constant. But in any universe which is expanding, and the redshift is due to that expansion, then the surface brightness per unit frequency goes down as 1 plus z cubed. And that's because the object was 1 plus z closer when the light was emitted, and therefore has 1 plus z squared larger surface area, and the time stretching reduces its luminosity, its apparent luminosity, by another factor of 1 plus z. So there's a very clear difference between the expanding case and the non-expanding case. What we did in the work that we published last year is we took near and far galaxies and compared their surface brightness. Now, to do that, we had to determine what their absolute luminosity was. So we could be looking at similar galaxies near and far. To do that, you have to assume a relationship between distance and redshift. And the assumption, the hypothesis that we made, which I proposed back in 2003 initially, was that it's a linear relationship for all z. Distance is proportional to z throughout all z. So there's a very interesting thing about that relationship, which is that it's almost identical predictions of luminosity versus z to the concordance model. Now, this is the plot of apparent luminosity versus redshift for supernova. And the top line, the dashed line, is the concordance model predictions with all the dark energy, dark matter, and all these other complications. The bottom line is simply the prediction on the basis of the static universe with a linear relationship between the redshift and the distance. So these actually correspond to a fraction of a percent, which perhaps you could say was an amazing coincidence, but we'll see. So what we did was we measured the surface brightness using the GALEX satellite for the near galaxies and Hubble, the ultra-deep field, for the far galaxies. We matched them so that the rest frame lambda and the luminosity was the same for all samples. So we had 8 samples at different distances in both the FUV and the NUV. And what we saw, what we were looking at, was only the brightest galaxies in the UV, which of course are the largest galaxies. These are very young galaxies with young stellar populations. We also matched them for the resolution, the linear resolution of the telescope, assuming the static model that we were testing. And that's important because if the galaxies are too small relative to the resolution, neighboring galaxies can blend together into an apparent galaxy. So we had to match the resolutions. So what did we find? What we were looking at, just to be clear, is we were measuring the apparent size and the apparent luminosity. So direct observables to get the surface brightness. Now mathematically, of course, that's the same as measuring the angular size at a given luminosity or the linear size in a given model. Well, what we found was, by gosh, the mean surface brightness of these galaxy samples is a constant. It doesn't vary at all with Z. And it doesn't vary from very low Z because each of those points is comparing the Z at low redshift and the Z at very high redshift. So it doesn't vary all the way up to a Z of 5. Now, of course, there are unresolved galaxies that are too small, and we took them into account too, because you can take into account the unresolved galaxies by simply using the median of the entire sample. And if you look at the median of the entire sample, then you get the exact same result. The surface brightness is constant, just as it would be expected in a non-expanding universe. Well, how constant is it? It's extremely constant, as you can see from this slide, well within the measurement errors and to a high degree of precision. Now, you can say, well, is this simply a result of the observational limits? We can only observe galaxies with certain range of surface brightness. Well, we tested this, and that's clearly not the case, because if you take dimmer galaxies, you can see where the surface brightness drops off the higher curve. To the right, it drops off because of observational limits. You can't observe things within when they get too dim. But for the brighter galaxies, the blue line that we observe, clearly there is not a cutoff. It's well within the observed limits. So our conclusion in this paper that was published last year is that the Tolman test is completely consistent with a static Euclidean universe, a non-expanding universe that has a redshift linearly proportional to distance. So what's new here is, and what we hope to publish soon, is let's compare the same data with the concordance model of the universe. Now, people, of course, are aware of the size data, and they interpret that within an expanding universe model as a growth in these galaxies. Now, we're talking with these spiral galaxies in basically a growth in their size at their birth. So, getting bigger babies with time. And there are theoretical predictions that were made based on h of z, that is the radius of the universe at a given time relative to its present radius. And these black lines show the theoretical prediction, which is anywhere between a slope of 2/3 and a slope of unity of the logarithm of the size, which is plotted against the logarithm of h of z. Now, how does the data we just saw stack up against that when it's translated into the expanding universe model? And you have to, of course, put in the factors that are assumed for surface brightness dimming and for the apparent expansion of their size. These are the same data points, just interpreted in this way, for the spiral galaxies. And as you can see, first of all, they fall well outside the theoretical predictions, And second of all, they don't even look like a power law. They don't look like a straight line. They look like some sort of curve. Now, those are our data. Just recently, I looked at the data for elliptical galaxies. And this is not based on our data. This is based on the data of Trujillo and others. And if you plot elliptical galaxy size in the same way, you see that they fall, again, well outside the theoretical predictions. And they also seem to be sort of a curve. Well, maybe this is just an illusion. Let's see what happens if nonetheless we say, all right, theoretically there should be a power law relationship between h of z and size. Well, let's plot the best fitting power law to this spiral galaxy data. And we get, of course, a slope that is, again, well outside the theoretical limits. And also, as you can sort of tell by eye, it is a terrible fit to the data. There's statistically, given the statistical errors in these samples, about a 1 in 4 million chance that this data actually fits that line. And of course, that's pretty much a 5 sigma result. So it's a terrible fit. Now, if we try to fit the elliptical galaxies, we see that they can be fit by a straight line. There's a smaller range in redshift that helps, but again, they're even further from the theoretical predictions. This basically means that the size of the elliptical galaxies, now these are very old galaxies, so we're talking about the growth of individual galaxies over time, in this model would be proportional to the h of z to the 1.6 power, much faster than the expansion of the universe. So what happens if on the same graph we look at the predictions of the static universe model? And static, by which I mean simply non-expanding. It can very well be evolving, but it's not expanding. Just like our Earth is evolving, but not expanding. So if we look at the prediction, it's a very simple flat line at 0. In other words, there is no change in size with redshift. So we look at how does the data fit, both for the ellipticals and the spirals, and it looks like a pretty good fit. How good a fit? Well, it's really an excellent fit. As you can see by these numbers, the slopes of these curves, of these lines, in the static model is a tiny fraction of the slopes assumed with the expanding model. So if you take the hypothesis that the universe is expanding, and that it is simply two more astounding coincidences that those points move to that flat 0 straight line, you're talking about a very big coincidence, approximately a 5 sigma coincidence. So basically, size evolution in an expanding universe simply does not explain these results. First of all, you have these coincidences that add up to a few chances in a million. Second, an evolution rate that itself changes with h of z as we approach the present epoch. You have 3 more parameters needed to fit this data in the expanding universe than in the non-expanding case. You have the same problems with ellipticals, where they're supposedly growing, as with spirals, which are supposedly larger and larger at formation. You have the question of where did these extremely large, dense ellipticals, thousands of times denser than galaxies today, where did they go? And finally, you don't have any physical mechanism that could produce this growth. The merger mechanism, whether it's small mergers or large mergers, you need about 20 to 40 times as many mergers as we actually observe in the real universe. So we can conclude that the surface brightness and the luminosity data alone are strong evidence against any expanding universe model. But the concordance model is obviously a lot more specific than just any expanding universe model. And there's more evidence against it as we get more specific. So, to start on that second part of the presentation, let's look at the fact that this is a hot Big Bang model. So it hypothesizes that the universe went through a stage that it was extremely dense and hot. And there's a big problem with that observationally. The predictions for thermonuclear production in that hot Big Bang of both lithium and helium are clearly wrong. That's most obvious with the case of lithium, and this has been actually known now for decades. As you get to stars that in our galaxy that are purer and purer in terms of iron, and therefore were formed earlier and earlier in the history of our galaxy, you get to what's called the spike plateau, which is that plateau on the right-hand side of the graph. The spike plateau is a consistent level of lithium, which is a factor of approximately 4 below the theoretical horizontal line, which is the prediction of the hot Big Bang model. So there's far less lithium than would be predicted in a pristine galaxy before any star formation has taken place. Now, if you go to purer and purer, less and less iron and purer stars, the problem gets worse because the spike plateau sort of starts to melt down. There are stars with considerably less lithium than the spike plateau. And if you get beyond a few thousand times less iron than our sun, the spike plateau disappears, and you get less and less lithium as you go to the left-hand side of the diagram, all the way down towards 0. So the evidence is completely inconsistent that lithium existed before stars started to form in our galaxy and supernovas started to produce iron and similar elements. It's completely consistent with there being no lithium produced, which is inconsistent with a hot Big Bang. If we look at helium, we see exactly the same pattern. This is determinations of helium plotted against the overall metallicity of the stars. Again, pure, presumably younger stars formed when the galaxy was younger are further to the left. And what you see is as you get to the purer and purer stars, there's a sudden shift in the slope of the buildup of the heavy elements versus the buildup of helium, and helium starts to drop away again towards 0, well below the theoretical level of approximately 25%. And the authors of this work were very surprised by this result, rejected this result in fact, and tried to use homology models to see whether they could reinterpret this data. And the homology models, a very different way of determining the helium abundance on the right-hand side of the diagram, came up with exact same results. So in both cases you have that in nearby stars in our own galaxy, the purer the star is, the earlier it's formed in the galaxy's history, the less helium there is. Now this is completely consistent with a galactic theory of element formation, which was proposed by many people before me, but I elaborated in 1988 based on specific plasma predictions. And if you take plasma predictions of the formation of the galaxies, you come up with a lot of intermediate mass stars, which are too small to produce lots of heavy elements, but produce lots of helium. And stars are also capable of predicting lithium in the right proportions. The lithium and helium abundance are strong evidence against any hot Big Bang model. Now, obviously, the concordance model is more specific than that. We also know that it involves dark matter. And there are problems that you'll be hearing about all day with dark matter. One problem is there isn't enough of it. Since dark matter is supposed to be observable through its gravitational influence, we can look at the local universe and measure how much gravitating mass there is. And as in this diagram and in many such studies, if you look at the local universe, you end up with a maximum of about equivalent of 0.1, 1/10 of the critical density, which is very far from the 3/10 of the critical density that the concordance model predicts. You also have problems with large-scale structure, with structures that form too early in the putative history of the expanding universe and are simply too large to form in the amount of time since the Big Bang. But again, in a non-expanding universe, you can put together electromagnetic forces and gravitational forces, and you can actually predict, and I did over 20 years ago, the size and dimensions of stars, clusters, galaxies, clusters of galaxies, and even superclusters of galaxies. And of course, in a universe that does not have an origin in time, you have enough time to form these large structures. Large-scale structures are, again, strong evidence against any dark matter universe. I don't really have time to go into this in depth, but of course, there are also contradictions to the hypothesis of an inflationary universe, which is fundamental to the concordance model. An inflationary universe should produce a cosmic background radiation that is completely random, but the cosmic background radiation we observe has large-scale alignments, which are very contradictory to the inflationary model. In addition, there is evidence in our local universe within 200 megaparsecs that the universe is not transparent to radio frequency waves, to the waves that constitute the cosmic background radiation, because the correlation of radio waves with infrared actually declines with distance from our position, which would only be possible if there is an absorbing or scattering medium. That's inconsistent with the cosmic background radiation coming from an inflationary Big Bang. So if you put all these things together, the surface brightness data, the large-scale structure, the lithium and helium, and the alignments of the cosmic background radiation, you have enormous amounts of evidence against the concordance theory. Some of this data has been around for 20 years. Some of it's very new, some of it's from last year. But it's been accumulating for more than 20 years. And as Mike Disney, who made this chart, points out, one of the fundamental problems with the concordance model is that it simply expands the number of free parameters every time there's new conflicting observations. And in fact, the number of free parameters has always been more than the number of independent observations, which means the theory has no predictive value. And as we all know, science is only useful if it has predictive value. So to sum up, at the moment we have a very popular expanding universe model that has very low predictive power, many contradictions with observation, many free parameters, and we have a much less popular non-expanding model with very few parameters and with high degree of predictability. In conclusion, I think it's time to switch. Thank you very much for your attention.
So we have a few minutes for a question. A question, how do you explain redshift then in a static universe?
Well, as I say, I think observationally there's a very good case that redshift is proportional to distance. Since this isn't due to expansion, we have to hypothesize that this is something that happens to light as it travels through space. So this is a new hypothesized modification to Maxwell's equations. Now, the benefit of this hypothesis is that it can be tested experimentally within the solar system. If we take spacecraft, such as the proposed LISA spacecraft, that are orbiting approximately 5 million kilometers apart from each other, and whose locations are carefully measured, we already have instruments sufficiently sensitive that we could directly measure the redshift between those objects. If this is something that's happening to the light, then we expect it to be happening within the solar system. If it's an expansion of the universe, of course we know that that expansion only affects non-gravitationally bound objects. Our solar system is gravitationally bound. Nobody thinks it's expanding. So that test would be negative. There would be no observed redshift if the redshift was due to expansion. So that sort of what you could call tired light or energy loss of light hypothesis could be tested experimentally.
Okay, Eric, I think you replied more than enough. And we have to move on to the next speaker. So we thanks again, Eric.
Okay, thank you.